In this video, we continue with where we left off last time, which was discussing how to find the zeros of a polynomial function. Remember that last time we talked about the fact that we can use the factor theorem to test whether or not a factor truly is a factor by using long division or synthetic division and checking if our remainder was zero. Well, the question that you might have been having is, okay, that's nice, but what about if I don't have a factor to check? Where do I even begin? Great question. Today we're going to answer that question with something called the rational zeros test. Let's get started. The rational zeros test allows us to check for all possible rational zeros of a polynomial function f. So if we have a polynomial function, f of x, in our descending order with a n x to the nth power as our leading term and a sub 0 as our constant term with integer coefficients, it turns out one of the things that we discovered was that we can actually form all possible rational zeros by making combinations of the coefficients of the leading coefficients factors and the constants factors. The way we express that typically is with p over q. That's a nice ratio that is describing all possible fractions formed by taking the factors of the constant term. Let me grab a color here. How about blue? So if we take a look at the constant term there, and we take that number, whatever it is, and we take its factors, that will give us our p's, our factors of our constant term. Similarly, we're going to take a look at our leading term and its coefficient, a sub n. So for example, I'll use red for that one. If I have a leading term in front here, a sub n of x to the nth power, whatever that coefficient is, I'm going to factor it and use that as my possible denominators for q. So that will be our factorization of our leading coefficient, q. That looks kind of strange to us so far. Another way that you might want to say this is to get all possible rational zeros, we would simply take the factors of the constant term divided by the factors of the leading coefficient, being careful to account for every sign possible, positive or negative. So we typically indicate that with our plus or minus symbol. So let's take a look at one, put it into context so this makes more sense for us. Suppose we have f of x equals 6x to the 6th power plus 5x to the 5th power plus x minus 12. Well, in this situation, we have a degree 6 polynomial, so we've discussed in previous videos how that degree tells us that at the ends we will be going in the same direction because it's an even degree. We also know because the 6 is a positive 6 and not a negative 6, that they're both going to be going up as we go left and right forever, so we know that. But as far as those x-intercepts, how would we even get started for checking? Well, here's our possible way of doing that. We can use our rational zeros test. We would start off with our factors of our constant term, negative 12. So looking at our constant term, negative 12, some factors of negative 12 include 1 and 12, 2 and 6, and 3 and 4. If I were to write those in increasing order, I would have, for example, for my p, positive or negative 1, positive or negative 2, positive or negative 3, positive or negative 4, plus or minus 6, and plus or minus 12. Those are all the ways that we could possibly factor the number negative 12. If you're wondering about the plus and the minus, remember that to get a product that is negative, the signs had to be different. So for example, you have positive 1 with negative 12, or you could have negative 1 with positive 12. That's why we need both signs. Now let's take a look at the factors of our constant term, 6. Not our constant term, our leading coefficient term, 6. Excuse me. All right, let's take a look. So for our q, we're going to be thinking about all the ways that we could factor that leading coefficient 6. Well, try it yourself. That's right. 1 and 6, 2 and 3. So this would mean plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Now this can look a little confusing to someone who's never done this before, but the idea here is we're just visualizing all possible numerators over all possible denominators. The actual set of possible rational zeros would mean we'd have to form all possible fractions with those numerators and those denominators that we've listed. So for example, one option, if I take a look here carefully, Let me grab maybe white here for us. One option for a possibility for a rational zero would be to take the numerator, positive or negative 1, and to divide it by each of the denominators below. So positive and negative 1 divided by plus or minus 1 would in fact be plus or minus 1. So for our set of possibilities here, plus or minus 1 is our first possibility. What's another option? Well, we could take 1 divided by the second denominator, 2. So that would be plus or minus half. That's another possibility. Another option is to divide that same 1 by our next denominator, which is 3. So plus or minus 1/3. We can continue this process, and you'll see that some of these will actually repeat. So the next one is also new. We have 1/6, so that's new. But as we move beyond 1, we can go to our next numerator, and that would be 2. 2 divided by 1 is new. That's going to be plus or minus 2. 2 divided by 2, however, is just 1, and we've already mentioned that, so we don't need to write that again. 2 divided by 3 is going to be 2/3. 2 divided by 6, that reduces, you're right. That's 1/3. But we've already mentioned that, so no need to do it again. And we continue with this, making sure to divide each numerator, potential numerator, by each potential denominator. So in the end, let me erase our work here so we can have some space. Let's take a look at what our answers would end up becoming. Make that a little bit bigger so I can go faster for you. There we go. Okay. So in the end, what our answers should look like for our possibilities, after we did 2/3, we should end up with plus or minus 3, plus or minus 3/2, plus or minus 4, plus or minus 4/3, plus or minus 6, and plus or minus 12. I encourage you to try that on your own. Maybe pause the video, check, make sure you understand where these numbers are coming from. We're simply dividing every potential numerator by every potential denominator, every potential p over every potential q. That would be our set of possible rational zeros. Now, what I don't want you to assume is that that's the list of all possible x-intercepts. Not quite right. This has narrowed our focus in our graph to any x-intercept which is a rational number, meaning a number that can be written as a fraction or a decimal which has a termination. For example, we could have an x-intercept like square root of 2. That's not going to be rational, so that would not appear in our list. But once we have a list of possible rational x-intercepts, we can start testing those using synthetic division, by plugging them in directly to the function for x and seeing if the remainder is 0, or even long division if we prefer. Once we find one, we'll start to stumble upon any other zeros, which may be irrational or maybe even imaginary. All right, let's check our next example. Example 1 says, can we find all possible rational zeros of the function f of x equals x to the third power plus 3x squared plus 2x plus 6? Now this is a nice degree 3 polynomial, which technically, to be honest, is possible to be done by simply factoring. So we could factor this by grouping. If you want to pause the video and try to factor by grouping and see if you get to the same answers in the end, that would be a good reminder of how you can do that, right? Group 2 of them together, find the greatest common factor, and continue from there. But imagining that this was a more difficult polynomial, we wouldn't necessarily see a factorization right away. So instead, the only place to start would be to find our list of possible rational zeros. So let's take a look. So if we take a look at our constant term 6, that's like our p, right? The possible factors of that constant term would be 1 and 6 and 2 and 3. We've seen that number before. So 1, 2, 3, and 6 with different signs, right? What about for the denominator? Well, the possibilities here are actually quite nice because our leading coefficient is just, you got it, 1. So if our leading coefficient is implied to be 1 here, and the only way to factor a 1 is 1 in itself, that means if I were to take a look for my q here, all possible denominators, we only have one possible denominator, and that is 1 itself, which makes our set of possible rational zeros quite easy, because to divide by 1 is really going to just give you your numerator, right? So our possible rational zeros, dividing 1 by 1, we get positive or negative 1. And then 2 and 3 and 6, etc. So we get positive or negative 2, positive or negative 3, positive or negative 6. Now, it could be the case that one of these is actually a real x-intercept for our function's graph, and we could verify that. In fact, by checking a look at this one, which factors, let's just do that real quick. If I were to try to factor this by grouping 2 and 2, I would have had, in factored form, f of x equaling x squared, our common factor from our first two terms, times x plus 3. And then from our last two terms, the common factor is, that's right, 2, leaving me with x plus 3 next to it as well. So that one does in fact factor. Can you remember what those are? Yeah, that's right. The x plus 3 comes in front because that's what's in common. And what's next to it would be the other two parts, x squared plus 2. Now what's interesting about writing it in factored form here, this one was a nice easy one that can be done like that. Now that it's in factored form, we have our factor theorem that we talked about in our previous videos. With that factored form, we could then set each factor equal to 0 to find our x-intercepts. And we can see here that x plus 3, if it were set equal to 0, wouldn't that give us that x is equal to negative 3, which is in fact one of our possible rational zeros that we talked about. So in this particular case, if I had started using synthetic division perhaps to test positive 1, negative 1, positive 2, negative 2, we wouldn't get any result with a remainder of 0 until we chose negative 3. And at negative 3, plugging that into synthetic division, or long division, our remainder should be 0. The other term, or factor rather, x squared plus 2, we'll talk more about that in a future video where we talk about imaginary zeros. Because in this case, if you were to look at x squared plus 2 and set it equal to 0, take a look at what happens. Wouldn't that mean that x squared would have to equal negative 2? But that's not possible if x is a real number, because when you multiply something by itself in the real number system, it should stay positive, right? Whether it's a negative times a negative or a positive times a positive, it can't become a negative result. So this would produce an imaginary situation. And so we'll study that in a future video. But for now, I wanted to show you in context how this rational zeros test would give us a place to start, and then with synthetic division, we could check whether or not we truly have an x-intercept. All right, let's try another one, but this time, instead of just finding the possibilities, we're actually going to see which of them does in fact produce an x-intercept. Example 2, it says find all rational zeros of the function f of x equals 2x cubed plus 3x squared plus 4x plus 6. Okay, so we have another degree 3 situation, which again would mean that we would have at least one real zero, one real x-intercept, since odd degree means we have an end behavior going in opposite directions, right? So we have to cross the x-axis at least one time. So we're guaranteed at least one x-intercept, but we're not necessarily guaranteed that it is a rational zero. It could be irrational. So let's get started with our list of possibilities. Take a look again at our constant term. We've dealt with that one before. So for our constant term here, p, our possible factors of 6, again, are 1, 2, 3, and 6. So plus or minus 1, 2, 3, and 6. And for our leading coefficient, we have a 2, which means that our q, our possible denominators, would include factors of 2. Well, that's just 1 and 2, so plus or minus 1 and plus or minus 2. So our list of possible rational zeros would include all possible fractions with those numerators and denominators. So let's take a look at what that would produce. I encourage you to pause it at this point, try it on your own, and come back and check. All right, let's see what we have. In this set of possible rational zeros, I would have 1 over 1, so that's positive or negative 1. I would have 1 over 2, so that's positive or negative 1/2. I would have positive or negative 2 over 1, which is just 2, plus or minus. I would have 2 over 2, which is just 1, but we've already mentioned that. I would have plus or minus 3 over 1, which is just positive or negative 3. I would have plus or minus 3 over 2, which is new. And I would have, let's see what else here, plus or minus 6. Yeah, that's right. And then 6 over 2 is just 3, but we have already mentioned 3. So it looks like we have positive or negative 1, positive or negative half, positive or negative 2, positive or negative 3, positive or negative 3/2, or positive or negative 6. That's still quite a lot to test. So if I was doing this by hand with no technology at all, I would have quite a bit to test. Positive 1, negative 1, etc., all the way through. But if I had access to technology, and I have included a Desmos link on this slide in your notes, so feel free to click on that and take a look if you can find the x-intercept on the graph right away. If you found it right away, you could then use that in synthetic division to continue your process of finding more zeros. I will save us some time and tell us right now, and again, you can see it from the graph if you check, that the one that will work should be negative 3/2. So let's take a look at what happens with negative 3/2. Using synthetic division, negative 3/2 going into our original polynomial function with leading coefficient 2, followed by the coefficient 3, then the coefficient 4, then the coefficient 6. We don't have any skipped terms this time, so no need to put a 0 anywhere. And remember this algorithm? That's right, we dropped down the 2. Then we multiplied by whatever was in the box. And negative 3/2 times positive 2, the 2 should cancel, giving us negative 3. We add down. Negative 3 and positive 3 added together, that's 0. We multiply that by what's in the box, that's 0 again. We add down, the algorithm said. 4 plus 0 is still 4. Then we multiply, again the algorithm repeats, we multiply by what's in the box. 4 times negative 3/2, well, the 2 goes into the 4 2 times, making it negative 3 times 2, which is negative 6. And here we are in luck. We have a remainder of 0. So again, if you didn't have your professor telling you, here's one that works, you would have gone through each of them, testing negative 1, testing positive 1, until we got to negative 3/2, where we finally would get remainder 0. Once we have a remainder 0, we know that negative 3/2 is in fact a real 0. And if it's a real 0, we have a real factor. Factor theorem says that we could write f of x in factored form now, where our factor would be, for negative 3/2 as a 0, x plus 3/2. Well done. Because our factor theorem says if c is a 0, then x minus c is a factor. That's it. But what's next to it? Remember, that's our quotient down here. The quotient is going to be what we get when we use those numbers at the bottom of synthetic division and we make them the coefficients 1 degree lower since we divided by a linear factor of degree 1. So we would have 2x squared. We would have plus 0x, but that looks tacky, so I'm not going to write that if you don't mind. And then our constant would be 4, so plus 4. So in factored form, we could say that we have something like f of x equals parentheses x plus 3/2 times parentheses 2x squared plus 4. Technically, that is true, and you could continue directly from there trying to find your next potential set of zeros. And we can do that by letting 2x squared plus 4 equal 0. So feel free to jump right to it at that point. But I will point out that if you were trying to get this in a nicer looking version of the factored form, you might notice that the 2 is also found in the term 2x squared as well as in the term of 4. They have a shared factor. So if you were to factor out the GCF, your greatest common factor, you could have written your factored version of f of x as 2 parentheses x plus 3/2 times parentheses x squared plus 2. Now, why would I do that? That sounds like more work, right? But if you pay really close attention, do you see what you could do with that 2 now? Yeah, you moved it in front, but couldn't you now redistribute it back into the first binomial? Why would you do that? That's right, because you would get rid of the fraction. You would actually have, as your function in factored form, 2x plus 3, because 3/2 times 2 is 3, times x squared plus 2. Now, some of you might be thinking, hey, I've seen that before. I already factored it from the very beginning. If you had done that by factoring by grouping, That's what you would have received as your result, right? You would have seen that already. Okay, so why did I go through all of that? To make it look prettier, yes, but also to make our lives a little bit easier, because I'm asked to find all rational zeros. We already found one of them from our list. We confirmed that -3/2 was in fact a zero, and it was a rational number, so it was a rational zero. But to find any remaining zeros, what we could do is set this factor, either at the beginning or in the cleaner version, equal to 0. So if you let x squared plus 2 equal 0, we've talked about this a little bit already today, that if you try to solve that for x, you'd get x squared equals -2, which would mean if you take the square root of both sides, x could equal positive or negative, because you always take the plus or minus square root, of the square root of -2. But that negative underneath, that can't happen, can it? So we know that's imaginary, meaning that we would really have as our answer here plus or minus I times the square root of 2, or plus or minus the square root of 2i. So those would be our two imaginary results. Now, if the question was asking you, back at the very beginning here, if it was asking us, find all zeros of the polynomial function, then we would have three to talk about. The rational zero, -3/2, and these two imaginary zeros, plus and minus I square root 2. But since they only asked me for rational zeros, it turns out that we've exhausted our rational zeros. There's only one of them, and it is -3/2. So our solution set would simply be -3/2 inside. That would be our final answer for this type of problem. All right. Well, I think that's it. Yep, that's it for our example videos today. I encourage you to practice this on your own and get ready, because next time we're going to be finding all zeros of a polynomial, not just rational. But we need to have this part really, really sound before we move on. So remember, practice, because math is not a spectator sport. I'll see you next time.